Hopefully this gets me. There's absolutely no feedback here, so.
Oh, is this okay? Say something. Okay. All right, everybody, we're going to get started here. Cece couldn't make it today, so I'll be doing the announcement. Our first speaker for today is Andrew Stillwell. Andrew received his Bachelor's of Science in Electrical and Computer Engineering at the University of Missouri-Columbia in 2005. He spent over 7 years at National Instruments in Austin, Texas, working in research and development on a wide variety of data acquisition products. He received his MS in Electrical Engineering at UIUC in 2015 and is currently working towards his PhD with Dr. Pawlowicz-Podgorski. His research interests include data center power delivery, switched capacitor converters, and inverters for solar and motor drive applications. Once upon a time, he had hobbies and free time. Now instead, he has 2 children, ages 5 and 3. Please join me in welcoming Andrew.
All right, thank you. Let's get started. So, Kevin, can you see if you can get rid of the part up top so we can see some titles? Okay, well, we're talking about that. So the motivation of this is looking at power converter density and specifically flying capacitor multi-level inverters or the flying capacitor topology. When you look at this topology, it's very attractive for inverter applications, high step down. Recently, high step up has been demonstrated very well. But it's also the core inverter technology we use with Google Littlebox. And one of the challenges we ran into with Google Littlebox is you've got 2 wires going in and 2 wires going out, power in, power out. What's not going in is 5 volts, which is what we typically are just supplying from a lab. So we had to put in helper circuitry to basically power our microcontroller and everything else. So for this Google Littlebox design, you can see the transformer outline there. That's our auxiliary power supply. We took 400 volts and basically used a flyback converter to generate 12 volts to power the fans and everything else. So there's many of these applications where you have to power the control, you have to power the gate drivers, maybe you have some secondary load like fans or something along those lines. And in all of those cases, you need to find a way to power that either from the output or the input. So in the traditional case, you look at, this is looking at the Google Littlebox case specifically. You have an input of 400 volts, you have an output of 240 volts AC. One option is to take this from the input, take 400 volts and step it all the way down to say 12 volts or 5 volts. But this means that that auxiliary power supply has to have very high ratings. It has to do an extremely large step down, which usually means it's not a very efficient converter. There's lots of solutions out there, but they're pretty bulky. Usually you're talking about a pretty sizable transformer. The other option is to take it from the output. So we have 240 volts. We could take an output charger, which we discussed very briefly, to provide 5 volts or 12 volts, something along those lines. The challenge there is, again, you're talking about a high rating. You're talking about AC to DC after you've already gone DC to AC. And then your efficiency is taking a hit because you're basically going all the way input to output, basically converting back in. And then you've got startup. So you kind of have a little bit of a chicken and the egg. You need your auxiliary power to start your converter and run all the control, but you need power getting to your auxiliary power in order to do that. So startup from that standpoint is very challenging. So the question is there a way that we can take power from within the converter itself and do this a little bit better, do this more efficiently? And that's what this talk is about. So we're talking mostly about an integrated approach. I'll talk a little bit more about the operation of a flying capacitor multi-level and why it's important and why we can take power internally from it. Then some of the challenges that are introduced when you take some power from that converter. And then finally, we'll show some results and talk about some other challenges that arise from doing this and some future work. So talking about the flying capacitor, kind of the basic operation. In steady state, when you're doing step down, we'll talk mostly about a 5 level. It's a little bit simpler, not what was used on Littlebox, but illustrates the purpose very well. But basically, each one of these capacitors descends in voltage. So this is, say, 3/4 VN, this is half VN, this is 1/4 VN. Switches are operated in complementary fashion, so this is never on at the same time, this is on, same thing like that. And you can see pretty quickly that'd be a bad idea, you'd be shorting some capacitors together. Other operation is V out is equal to dVN, so very much like a buck converter, where you just have that one duty cycle that sets your conversion ratio. It's the same operation here. However, instead of bouncing between, say, 0 volts and VN, you're bouncing between these different levels that are dependent on your operation. So that's where you get these duty cycle ranges. And for the 5 level, there's these 4 ranges. You're bouncing between 0 and 1/4, 1/4 and 1/2, and so forth moving forward. So depending on where your duty cycle operation is, you're bouncing between these different PWM levels. So talking about the control strategy, there's what's typically used is what's called phase-shifted PWM operation. And it's pretty classic from what's derived from some of the first papers out there. But essentially what you have is you provide 4 PWMs, each one of them phase-shifted evenly, all of them at the same duty cycle. And when that happens, you get this nice operation. This is looking at the lowest level. This chart basically shows the output of the V-switch node, which from here forward, just think of it as a buck, and you're putting a PWM into it. And then over here is the charge and discharge of the capacitors, which is very important for balancing. And we'll talk about why that's important a little bit later. But to give an illustration of kind of how this operates, if you look at this first state, we've called it D1. There's one switch that's high. Basically, current flows through, and you're essentially just discharging your capacitor. So C1 discharges, you're in this operation state. When you go into D2, now you're charging C1 and discharging C2. When you go into D4, very similarly, you're discharging C3, charging C2. And then finally in D8, you're just charging up through C3. And then the final state is D0, where basically all of those bottom switches are on. And in that case, you're just grounding your output in that, to kind of reset. That provides your other level there. And you're switching between that each time. But in this case, no current is flowing through the capacitors. Now, a couple observations out of this. One is if you want an amp second balance on your capacitors, basically meaning that your capacitors are going to stay at a constant voltage throughout periodic steady state, you need to keep each one of these periods the same. So D2 equals D1, D4, and D8. And you can see that here. This time duration needs to be the same. This time duration needs to be the same. This time duration needs to be the same. So all the durations have to be the same in order for this to operate. But if you keep them all the same duty cycle, then your amp second balance is going to be maintained, and you don't have to worry about your capacitors drifting in time. Now, when you go to other duty cycle ranges, I'll show some of the tables for it a little bit later, but it's essentially the same operation. You're still going to have charge and discharge of your capacitors. You still have to keep that amp second balance. Your duty cycle can change, but the operation is very similar. Now, when we talk about the auxiliary supply, one of the nice things is we can take power from inside the auxiliary or the flying capacitor multi-level converter. So if you looked at this first node labeled Vox up here, it's either at ground or it's at a slightly higher voltage, namely Vn minus that capacitor voltage, which is 3/4 of Vn. So essentially that node is either going to be at ground or 1/4 of Vn. So think about before where we were taking 400 volts and then we were stepping it all the way down to 12. Now maybe we're stepping 100 volts and stepping it all the way down to 12. So our auxiliary power supply is rated for a much lower voltage, and we can have a much smaller converter, hopefully something much more efficient. The challenge now, though, is what about the flying capacitor balancing? We talked about how we have the amp second balance. Have we messed that up? And the amp second balance and the capacitor charging is important. We want balanced capacitors, because if our capacitors become unbalanced, we have higher switch ratings, we have higher capacitor ratings. We're also going to get some more harmonics in the inductor current, which we'll see a little bit later. So we do want to maintain this balance, and we want to actively do this. So to do this, let's look at the 2 different periods that are affected the most. So when you're looking at C3 during subperiod D4, basically C3 is discharging with IL. But now during D8, C3 charges with IL and IOX. So we can see that in this equation here. So now instead of just IL charging and discharging, now we have IL going in as well as IOX, and we only have IL discharging. So if these 2 periods are the same like they were before, if D4 is equal to D8 is equal to D, then we have this relationship, and this can't be true. If IOX is non-zero, then we're no longer going to have an amp second balance on this capacitor, and this is going to cause a problem. It's also important to note that IOX doesn't flow through the other capacitors, so that auxiliary power doesn't infect the other capacitor charging as well. And furthermore, if we look over in D8, we can charge this capacitor completely independent of C2 and C3, so we have a degree of freedom there. active balancing, basically we're doing a couple things. We're adjusting the period of D8 with respect to D4 such that we keep an amp second balance on that first capacitor. So basically we're just tweaking the amount of time we spend in those two different states. At the same time, we still want to keep an amp second balance on C2 and C1. So we want to keep them balanced, so those durations all have to be the same. And then finally, we still want to be at the same converter duty ratio where we were before. The total DVN operation, we still want that relationship to hold. So we have to make sure that the sum of all of these is still the same. And in the end, we have a set of equations, and based off of where we want to be and how much current we're processing with IOX and IL, we can balance this out. There is some practical applications where once you start to take into account the inductor ripple, you do need to adjust the phase shifts, but that's something you can read in one of the papers. But essentially, we make D8 smaller, we make all the other ones bigger, and we keep an amp second balance on that first capacitor. Now, we can do this in simulation, and simulation kind of shows this out, right? So this is one where we've hung a resistor off of that node. We can see in the unbalanced case where we do normal operation, VC3 starts to climb. This is expected, right? We charge, we're putting more current into it than we're taking out. However, once we apply balancing, VC3 stays constant. It doesn't go up because we've basically balanced the current such that the average current is 0. Now, we can do these for all the other duty cycles. We talked about how the operations vary the same, but really the background, the idea is all the same. We're adjusting a duty cycle, and specifically we're adjusting the duty cycle of the first switch, S4, with respect to all the others. And we're making sure that we maintain the capacitor balance on the other two capacitors, so we're still continuing to keep those durations the same. Finally, there is some phase adjustments as well, because not only do you have to worry about the initial 4 duty cycles, but in this case, when you get to higher levels, you have duty cycles in every period that you have to worry about. But the operation is really the same. Now, how do we want to control this? One idea is we talked about we have IOX, the auxiliary power, we have the actual load current, and we can mathematically solve for the duty ratios. But in reality, you don't want to measure those currents and then try to calculate something out and then afterwards try to find the right duty ratios. You want to use control. So this just uses proportional control. It measures the voltage across VC3 and then adjusts those duty cycles accordingly. So if the duty cycle starts going a little bit higher, we know how to adjust it back down and basically balance out those capacitors. So it's a simple proportional control loop implemented digitally. We measure the voltage and then we let the microcontroller do the rest. For the auxiliary power supply, we didn't want to spend too much time on this because there's a lot of good solutions out there. So we used a TI simple switcher. It takes up to 60 volts input, provides a regulated 5 volts output or something along those lines. And then really simple configuration, so it's a feedback resistor. One of the challenges is that since you are putting this on that node, and that node is at Vn divided by 4, this becomes one of the limits on how much input power or input voltage you can place on this. So we designed this converter can only take in 60 volts. So the input power or input voltage can only be 4 times that, basically limiting us to 240 volts. If you wanted higher voltage, if you wanted to use this same auxiliary power supply, but use a higher input voltage, you could step up the number of levels in this, so a 7 level or an 8 level or something along those lines. Or you could just design your auxiliary power supply differently, but it is something you have to take into account. We did create a prototype for this. It's a 5-level. We're using GAN switches. This should be pretty similar to those that are familiar with the little box design. But again, using 240 volts input, this can do DC operation from 0 to 240 volts. It can do AC operation. It really depends on how you're modulating the duty cycle. Power is designed for about 600 watts, and then switching frequency is 120 kilohertz. We can do probably faster on this as well. It is important to note, I talk about startup a little bit later. It's located off-board. Startup at this point is really just a breadboard design that we've shown to work, and we'll include in another prototype later on. So let's talk about some results. When you look at this first one, this is with natural balancing. So we've hung a load off of that auxiliary node, and you can see a couple things. First, ideally, all of these levels would be the same. They'd all be at 12 volts. That would show good capacitor balancing and be representative of one that's well balanced. But you can see it's not. Also, we can see that since it's not, we get a lot of ripple in this inductor current. In this case, all the duty cycles are the same, so we're not applying active balancing. In the active balance case, you can see D8 has been decreased in time. Our balance is much better. Most of these are very close together. These three duty ratios are all the same because, again, we talked about we still want to keep the active balance on C1 and C2. If you look at numerical results, we can see on the capacitor stress on VC3, it did charge up some. Notice that it didn't continue to charge up because the flying capacitor has some natural balancing in there that does take care of some of these imbalances that are occurred with either timing, or in our case, we've kind of introduced an inherent imbalance. But it's still up there at 38 volts above that 36 volts where it would be ideal. And then this introduces some additional switch stress. So this sort of stress is over about 22% versus once we apply active balancing, it's about 7%. So it increases our switch stress quite a bit. And you can imagine as you start scaling up to higher voltages, this becomes more of a concern and something that becomes a benefit. Just to show it does work for other duty ratios, again, you can see this particular duty ratio is decreased. In this case, we actually end up increasing a different duty ratio because we're discharging a little bit more. Okay, so one of the questions that comes up is, okay, how much power can I take out of my auxiliary power? If you imagine what we're doing is we're decreasing this duty cycle, but is there a certain point where this duty cycle becomes zero? And at that point, we can no longer handle this imbalance. And the answer is yes, there are some limits. So for the 5 level, you can go through and derive basically based on a constant power, what are the limits of how much of the auxiliary power compared to the output power that we can provide. In the lower duty cycle, it's about 1/3. Once you get into these middle ranges, once you get closer to 50%, it decreases pretty significantly because the duty cycle you need to adjust becomes smaller and smaller while you're still providing power to the auxiliary power. So you kind of have a limited amount of regulation you can apply at that point. And then it goes back up near 75% and tails back off again. So what this really shows us is for a large step down, this works pretty well. If you're working in this duty cycle range, you're in good shape. If you're looking at an inverter operation where you're going across all these duty cycles, you might have to do some additional work to either buffer across these areas where you're not really able to supply power, or to schematically work around it by turning off the auxiliary power for a little while or working some other way around it. So startup, very briefly, one of the concerns with startup is where you supply this. What we chose to do in this case is take startup and feed it back into this auxiliary power. We could feed it straight to the microcontroller at 5 volts, but then we'd be doing a very large step down of say 200 volts or 240 volts to 5 volts. That's a really large step down, something that's really inefficient. But if we already have this auxiliary power supply here, we can feed that directly from our startup circuit, feed it at a much higher voltage, much higher efficiency, and it works pretty well. In this case, we're just using a current regulator. It supplies constant current, but it's rated to a very high voltage. And then we basically use a zener to regulate that and make sure that we don't go above that 60 volts. Because again, we don't want to feed something higher than 60 volts to this switch mode power supply. So some results. At this point, I don't have this integrated in with the multi-level converter. These are not a fully integrated solution, but that's something that I'm working on. But we were able to use the startup to feed the auxiliary power supply to start up a microcontroller. This is a step input of 200 volts. You can see that the intermediate voltage here stepped up to 50 volts pretty cleanly. And then once VDD met the threshold of the microcontroller, it powered on and started providing our PWM control. And you can imagine from there, you'd provide a power good signal that would turn off that other power supply, and we'd rely on active balancing from there moving forward. Okay, so conclusions. First off, we showed a 5-level flying capacitor multi-level with an integrated power supply. We showed that basically instead of taking from the input, we take it from a naturally occurring node inside the power converter itself, and we get a very big reduction in that voltage ratings of that auxiliary power supply. So in this case, a step from VN down to VN over 4. When we do that, however, it introduces this imbalance in the capacitors, and since the balance imbalance is something we need to get rid of, we applied active balancing to basically very carefully shift those duty cycles and keep an amp-second balance on all our capacitors. We showed a very quick implementation of startup. and then also showed some of the limits of where this technology goes and what kind of other additional considerations you have to worry about. For future work, full startup is definitely on the plate, and then trying to find some creative ways to work around these auxiliary power limits. So for acknowledgements, this work was funded in part by Sandia National Labs, and I'll go ahead and open it up for questions now. Thank you. Sure.
Thank you for the presentation. On your slide showing the different duty cycles, whenever you're doing active balancing, it looked like there might be higher ringing on the cycle where you're changing, where you're regulating the duty cycle, or where you're maybe supplying power to the auxiliary supply. Is that something you noticed?
I didn't notice it specifically. My guess is that's more of a result of either just moving probes around or measurement error, because there's not a schematically different situation on the switching that would really cause that to be that different. Now, if it's something that I consistently, if I look back and consistently see it, then I might be concerned, but I don't recall that being something that was very noticeable. It may have been in that shot, but I don't remember seeing it consistently across the measurements. Other questions? Sure.
When we've talked about this in the past, you mentioned that there are some good applications of this kind of idea, and there are some areas where this probably wouldn't be a good application. Could you kind of provide some of that, where this would fit and where this might not fit in line?
Yeah, my main concern is right now, probably because it's what I've been focused on the most recently, is that those power limits. If we can't regulate at 50%, then it makes it very challenging with an inverter because you're sweeping across all those duty cycles, right, consistently, and you don't want your control power to black out at 50% duty cycle. I think there are solutions for that, whether it's beefing up the auxiliary power supply with a larger input capacitance so you can kind of buffer across that, or maybe some more advanced control there. But that right now is a pretty big concern. For step down, I think this is a really good fit. The challenge there, though, is if you're already doing a large step down, why don't you, if you're stepping, say, 400 volts down to like 10 volts or something, then what's the difference between taking that 10 volt output and turning that into 5 volts already? Then it's just a startup question. So that, it works well for step down, but maybe it's not as big of a benefit for step down. Actually, when you turn this around and look at it as a boost or a rectifier, like Z-Tau's work, since the current direction flips, you can process a lot more power, at least at that lower duty cycle. I haven't really mapped that out and done all the math on that, but I think that's also a promising application.
Thank you.
Yes, Dr. Palawa.
Yeah, I'm curious, you showed those with the magic duty ratios where it at 0.25, above 0.25 you have trouble regulating, and at 0.5 you get 0, and then 0.75.
Mm-hmm.
What does it look like for other, that's for a 5 level?
Yeah.
Is it just, is it 5 minus 1 divided by 4?
Mm-hmm. So
if you do a 6 or 7 level, there'd be different thresholds where you would have a hard time regulating?
That's correct. So the way we get away with, that's not the best way to phrase it. The way this works on those like the lowest level is you have a way to you have a specific state. Can you go to next slide 4? Let's go forward a little bit more. So in this case, you notice that the charging between the C3 is completely independent of the rest of this, right? So in the case where you're generating Vn over 4, there's no other charging going on while you're charging this D8. So you have an opportunity to independently charge and discharge C3. Some of the other states, like the case where you're at Vn over 2, there's no independent charge and discharge method there with those switch states. So the way you regulate that is by switching to this state, and you're completely reliant on how much time you have with these periods to compensate. Now, and for the 5 level, it just so happens that you've got 2 states and they're on each side of that, so you can regulate it in between. When you get to higher levels, certainly at the edges, you still have this mechanism. So you're always going to have, at the lowest level, you'll have this case, and at the highest level, you'll have a pretty good situation. In between, with higher levels, it gets more tricky. There are some cases, like with the 6th level, where you almost always have a case where you have this independent charge and discharge. When you look at the 7 level, you have to combine 2 states in order to get the independent charge and discharge, so it gets more complicated. And I haven't been able to do the analysis for that because the number of variables just keeps going up. And that's a much more, control gets much more complicated there, and the power processed, I think, is going to depend on which control implementation you choose there. So I think it opens up some degrees of freedom in good ways and bad ways. But it's something that we need to look into if we're going to look in this for higher levels. Someone's got to read it. So, yes.
Or is maybe a new master student?
Yeah, sure. Yeah.
So, for example, in our case, when there's a Dixon, when one of the caps are going on balance, every other cap at the same phase will go on balance at the same direction. But here you have multiple phases. Can you group them into let's say an odd phase, an even phase, and then predict, for example, if your C1 is going out of balancing, then C3 is also going out of balancing in the same direction. So you only read one capacitor voltage and you predict the other one.
So if you look at the work on natural balancing, it's not intuitive at all. And it uses a lot of math that proves that it works, but doesn't give you a lot of intuition on how to apply it or a lot of those rules of thumb as far as if this happens, then this happens. The capacitors are related. If one goes out of balance, it should be reflected in the others, but not in a very analytical way, I would say, especially once you start going up to a 5 level or a 7 level, that you would have a one-to-one relationship. The way we're able to just measure C3 here is because we're inducing an imbalance on that one. We know that there should be an imbalance on that one. We rely on natural balancing on the other 2, but we don't actually do any feedback or take that as an input. If you look at some of the results, the last capacitor does actually see a pretty decent additional voltage in the unbalanced case. But that's completely due to that natural balancing not operating well in that case, as opposed to something we're inducing, because none of the auxiliary current is actually going through that one. Does that answer your question? Okay. All right. Thank you.
Thank you, Andrew. So our next speaker will be myself, actually. I'm representing the IEEE, PES, PELS, IAS student chapter here at University of Illinois. And I'll be talking about engineering open house. You guys may have seen on the sign-in sheet going